This is Dr. Paul Worsey at the Rock Mechanics and Explosives Research Centre at UMR. The Research Centre is currently working for the Naval Weapons Support Centre on a series of washout tests of a selection of Navy and Air Force plastic bonded explosives. Part of this research program involves impacting these explosives with high pressure, high velocity water jets to ascertain the safe operational washout limits. Deflagration and detonation of similar explosives has been achieved at RARDE in England. In this work, an initiation of the explosive charge was accomplished with water jet velocities in excess of 1.6 kilometers per second using a half-inch nozzle. In our research program, a dual experimental approach is being undertaken. This consists, firstly, of small-scale investigation of the mechanisms involved in water jet initiation of PBX explosives. This experimental approach involves projecting small volumes of water at a very high velocity at explosive targets using a specially designed piece of equipment. It is this program that will be described in this report. The second approach involves large-scale experimentation to examine full initiation of charges. These experiments will be similar to the British experiments and will accelerate larger volumes of water through a large diameter nozzle using a high pressure intensifier. The equipment will be on loan from the British NCB. These tests, because they will be with full-scale charges, will be carried out at the Centre's research facility at the University Experimental Mine. The current work on high-velocity impact testing has evolved through a number of different water derringer designs. These designs are based on using a small explosive charge as the propellant. In these designs, the explosive charge is initiated by an exploding bridge wire detonator, which functions in less than 3 microseconds, thus allowing exact synchronization with our high-speed camera system. The development of the derringer can be seen through a series of schematics of the internal designs. All designs are based around a 3-component holder system, which consists of an outer casing, an inner explosives holder, casing and backstop, and the nozzle holder. In these designs, the inner 2 components are threaded to match the outer steel casing. After initial experiments, the first design was modified as follows. Firstly, due to the high brisance of the explosive charge, the nozzle holders were specially heat treated and hardened. In addition, to reduce the dynamic shockwave from the explosive, the charge was encased in a Lexan sleeve. As the water jet velocity was increased, in successive testing, larger water volumes and therefore larger explosive charges were required. Lexan spacers were set within the block to give this additional room. Film records indicate that there is a brief initiation of explosives at impact velocities above 3 kilometers per second. To more accurately analyze the initiation of these events, this gas chromatograph has been acquired from the Navy. In order to sample reaction gases without contamination from the explosives contained within the water derringer, a 3rd generation water jet driving device has been designed. This design incorporates a Lexan plunger and gas venting holes in the outer steel jacket. The plunger is designed to contain the water before firing, and then after firing to allow venting of the explosive gases. The plunger is designed to be of a tight fit such that no gases escape around it. Each experiment is performed in the explosive laboratory inside an 880 cubic foot explosion chamber. To record the impact events as described in the earlier videotape, a cording camera system capable of up to 1.25 million 24mm frames per second and a spin physics high-speed video system capable of up to 12,000 split frames per second observe the experiment through special viewing windows. Lighting for the camera comes from a photographic xenon flash. This unit is connected to the cording so that it synchronises illumination with the impact event. It is necessary to contain all the explosive fragments from each event so that they can be easily and safely collected. Originally, the aluminum table on which the derringer sits was contained in a static resistant bag, like this. This bag was sealed around the camera portholes with duct tape. However, this complicated the experimental setup. With the third generation waterjet driving device, where the driving explosive gases are vented, it is possible to confine the explosive target in a relatively small, clear plastic tube. In this setup, a graduated reference scale is included in the tube, which is sealed to the top of the waterjet driving device with O-rings. The target sample is cemented in a plastic ring, which is then glued onto an aluminum plate. The plate with the target is then placed on top of the clear plastic tube and is held in place with a jack. This method has been successful in containing all the target fragments. Over 60 water derringer tests have been performed to date, with velocities in excess of 4 kilometers per second having been achieved at nozzle diameters from 40 to 100 thousandths of an inch. Brief initiations have been detected. Here is one such example of a composition A3 showing indications of initiation. When compared with an intact sample, the reaction is clear. In comparison, here is an unreacted A3 sample which has suffered water jet impact at a lower velocity. At present, work is continuing at more closely identifying the velocity at which the initiation starts, and also to identify the point at which deflagration switches over to detonation. The development of the third generation waterjet driving device is coupled with the extended use of the gas chromatograph to analyse the chemical products being produced from the impact. Thank you for watching.